Hey, good morning, dear students. Today we'll continue with equilibrium concept, and we have studied some chemical equilibrium. Under chemical equilibrium, up to Lee-Chatelain's principle, we have studied, right? So now we'll take up ionic equilibrium. Ionic equilibrium, when I say the equilibrium existing between dissociated ions and undissociated molecules, right? That is ionic equilibrium. Under ionic equilibrium, various things, like acid-base theories to start with. Then we'll move on to expression for H plus OH minus ion concentration, concept of dissociation constant Ka and Kb, then ionic product of water, then concept of pH and pOH, okay, related problems which are very important. Later, it will be the concept of buffer solutions, Henderson's equations, calculation, buffer action, correct? And then solubility product, common ion effect, application of solubility product and common ion effect for salt analysis. So these are all some of the important things which is there under ionic equilibrium. So numericals are there under every concept. Okay, so fine. As I told you, equilibrium being one of the most important chapters from first piece. We'll take up next. Under ionic equilibrium, importantly, it is acid-base theories. The question, which substance is acid, which substance is base? The basic idea of acid and base comes from Arrhenius theory. And if we know acids are the substances which contain H plus, bases are the substances which contain OH minus, it is Arrhenius theory. Okay. So what is Arrhenius theory of acid and base? Acid is a substance which ionizes in water to produce H plus. Why did I stress ionizes? According to the theory, the atom or the substance has to ionize in water to produce H plus. If it doesn't ionize, it cannot be acid. That's the simple thing, right? So substances which ionize in water to produce H plus ion are acids. Okay. So if that is the case, we'll take what is base? Base is a substance which ionizes in water to produce OH minus ion. If any substance gives hydroxyl ion, it is O the base. If any substance which gives hydrogen ion, it is we call as acid level. We take some examples of acids. HCl when added to water, it gives H plus ion and Cl minus. Similarly, acetic acid will give acetate ion and H plus ion. Since they donate H plus ions upon ionization, they can be considered as acids. Similarly, base. When you add sodium hydroxide into water, it ionizes to give OH minus ion. KOH gives OH minus ion. So these substances can be considered as bases. So it's a simple theory and nothing else to add. Okay. But the problem with Arrhenius theory was any substance to be called as acid or base, it must dissociate in water to produce H plus OH minus. But there are certain substances which neither dissociate nor contain H plus OH minus, yet behave as acids and bases. Is it? What are the examples? Magnesium oxide is base. It doesn't contain OH minus. Aluminium chloride behaves as acidic substance. It doesn't contain H plus ion. Like that, some of the compounds you can always. Okay. Calcium oxide, base. Boron trifluoride, acid. Apart from that, certain substances behave as acids as well as bases. They are called amphoteric. The theory doesn't account for it. So the theory is most fundamental one. That doesn't mean that the theory is a total failure. The theory is applicable in case of substances which contain H plus and OH minus ions. Okay. Now, to account for acidic nature and basic nature of substances which are not under Arrhenius concept, another theory has been proposed called Lowry-Bronsted concept or Lowry-Bronsted theory of acids and bases. An acid is a proton donor and base is a proton acceptor. There is no question of OH minus at all here. Acid is a proton donor, base is a proton acceptor. Then what is a proton here? A proton is H plus. Then why do we consider H plus as just a proton? It is actually hydrogen ion. Why should we consider it as a proton? Anybody?
Hydrogen's electronic configuration has only one electron in it. So when it releases one electron, it becomes just a proton.
Exactly. So H plus ion contain a proton, nothing else. Okay. So when you take this hydrogen atom, atomic number 1, so proton number 1, there is 1 electron. And how many neutrons are there in hydrogen? 0. So if you remove that electron also, this poor hydrogen will be completely a proton particle, that's all. Okay. So 1 proton, electron 0, neutron 0. So that's why hydrogen ion is similarly a proton. Okay. And also you should know that this proton H plus, whenever it is formed in aqueous medium, it doesn't independently exist. So what actually happens, H plus would always rest on water. Okay. So how does it rest on water? Simply it will go and absorb? No. There is a hydrogen, coordinate bond which is formed between water and H plus ion. Okay. And thus H3O plus is formed. This H3O plus is called hydronium ion or hydrated hydrogen ion. Which is correct?
Hydronium ion.
Hydronium ion.
Yes.
Yes, sir.
Both are correct. Hydronium ion, hydrated hydrogen ion. So look at that. You need to get the meaning of it. H2O dot H plus. Hydrated salt waste. Like that, hydrated hydrated hydrogen ion. So hydronium ion is nothing but hydrated hydrogen ion. No problem. Going back to this. So according to this, proton donor, acid. Proton acceptor, base. Add acid to water. It dissociates to produce H plus. H plus is nothing but now H3O plus. So you can see here, HCl when added to aqueous medium, it dissociates to give H plus, which is nothing but here exists as hydronium. If there are 1000 H plus ions produced, there will be 1000 hydronium ions formed. So we directly represent H plus as hydronium. Okay. And HCl, after donating, it has become Cl. Okay. Now in this, people have to tell me which is acid, which is base.
HCl is acid, H2O is base.
H2O is base.
H2O is base. H2O is proton donor.
Except
Accept.
It is proton donor. Yes. Answer is given by me only. Now, acid is a substance which donates a proton. So HCl is acid. Base is a substance which accepts a proton. H2O after accepting a proton has become H3O plus. HCl after donating a proton has become Cl minus. Therefore, HCl is acid as it donates a proton. Water accepts a proton, therefore it is base. And come to the right hand side, product side. Water after accepting proton, it has become H3O plus, and that H plus is a guest which is there resting on water. It is ready to be sent out anytime. That means H3O plus is ready to donate that H plus. The one which is ready to donate H plus can behave as acid. And Cl minus has the negative charge. Because of that negative charge density, it is always ready to accept one H plus if anybody gives. The one which is ready to accept H plus can be a base. Thus, in this reaction, there are two pairs of acids and bases. The first, HCl, which is an acid, after donating has become Cl minus, which is behaving as a base now. Water, which is the base, which is ready to accept a proton, and after accepting it has become an acid. So acid 1, base 1 is first pair of acid elements. Acid base 2, acid 2 will be second pair of acid elements. Now, what is that important thing? Acid 1, base 1 and acid 2, base 2 are conjugate acid base pairs. They are called conjugate acid base pairs. Can anybody tell me what do you mean by conjugate acid base pair, if you remember?
The base and the acid and base pairs which differ by one proton.
So the acid and base which differ by one proton, not two. One proton. Okay, that is what is a conjugate acid base pair. Okay, now let us list out here. We'll take up HCl. After donating, it has become CL. Similarly, H2O, after accepting, it has become H3O+. So you can see they differ by a proton. So therefore, HCl is an acid, Cl minus is base. But what is the relation between them? HCl is a conjugate acid of Cl minus. Cl minus is a conjugate base of HCl. So H2O is a conjugate base of hydronium ion. Hydronium ion is a conjugate acid of water. So there is one secret in conjugate acid base pairs that we should always know. What is that? Stronger the acid, weaker is its conjugate base and vice versa. Okay, stronger the acid, weaker is its conjugate base. Now people have to tell you, HCl is strong acid or weak acid, as you know.
Strong.
HCl is a strong acid. Its conjugate base therefore should be
Weak.
weak base. So HCl is a strong acid and therefore Cl minus is a weak base. In case of water, water itself is a weak electrolyte, very weak electrolyte. So if you consider it as a base, it is a weak base. So obviously H3O plus can be strong acid. Okay. Now we'll proceed. That's what I have shown here, no problem. Similarly, in case of acetic acid is an organic acid. All organic acids are weak acids. You can generalize that. Its conjugate base is acetate ion. Acetate ion is therefore strong base, strong conjugate base. Okay. So now let's do some more exercise. Before that, I want you to give conjugate acid or base of the following. Okay. I'll take, give me conjugate acid of this.
CO minus.
You want acid.
HCO.
For example,
Formic acid.
Formic acid.
look at this acid if you want. Now we'll take this HCl itself. You take this HCl case. You can see HCl is acid. If you want base, what did you do? Remove a proton. If you want acid, add a proton. Now we want conjugate acid of Cl minus. So what we can do? Add a proton. So remember this rhythmic sentence. Acid, add a proton. Acid, add a proton. Acid, add a proton. Base, remove a proton. Acid, add a proton. Okay. I want conjugate acid of formate ion. Huh? You told. If the people should be interactive, please. Give me conjugate acid, man.
HCO.
Formic acid.
Formic acid.
Formic acid. Okay. Give me conjugate acid of Cn minus.
HCl.
HCl.
Give me conjugate acid of NO3 minus.
Nitric acid.
HNO3.
Nitric acid. Give me conjugate base of benzoic acid. Benzoate ion. Benzoate ion. Right? Give me conjugate acid of NH3. Give me conjugate acid of NH3.
NH4
H.
Ammonium.
NH4. NH4 plus.
Ammonium. Correct, no? Give me conjugate base of sulfuric acid.
H2SO3.
HSFR.
HSO.
Remove a base, remove a proton. After removing H plus, there minus remains, right? HSO4 minus. Give me conjugate acid of bicarbonate.
Carbonic acid.
Carbonic acid.
H2CO3.
Carbonic acid. Give me conjugate base of bisulfate.
Sulfuric acid.
SO4.
SO4 minus.
Give me conjugate acid of carbonate ion.
HCO3 minus.
Bicarbonate. Like that. I'll point out now. You have to tell me that is weak acid or weak base. Okay. Early morning, this video is lagging. I am already in Bangalore. The video is in Tumkur. Now listen. See, I'll just point out a molecule. I'll switch off. I can't see this video. Afterward. See, you come to this first case. I'll just point out a substance here. You have to tell me whether it is a weak acid or weak base or strong acid, strong base, something like that. Okay. Yes. Yeah. You can see I'm pointing out. Why so much time? HCOOH. Is
Weak
it
acid.
organic acid or inorganic acid?
Organic acid.
Organic.
Organic
Organic.
acid. I just now told you, no. Organic acids are.
Weak acids.
Weak
So
acid.
tell me, formic acid is weak acid. Formate ion.
Strong base.
Strong base.
Strong base.
Now I'll randomly point out.
Weak base.
Strong base.
Strong base, sure,
Weak base.
strong base.
Weak base. Weak base. Strong acid.
Strong.
Weak acid. Weak acid.
Weak acid. Weak acid.
Weak acid.
Ammonia is a weak base. Actually, in water, ammonia, when dissolved in water, it gives ammonium hydroxide. So ammonia is nothing but ammonium hydroxide, you can mean. So it is a weak base and it is strong acid. And therefore, and vice versa. So HCN, CN minus is strongest for the reason that HCN was weak acid. So this is weak base for the reason that this is strong acid. And what about benzoic acid? Weak acid. Therefore, benzoate ion should be strong base. Okay. This is weak base, strong acid. Like it goes. H2SO4 strong acid, the bisulfate ion will become weak base. And again, sulfate becomes, if that is strong acid, then it becomes weak acid, because when it donates a proton, then it becomes strong base. between bisulfate and sulfate, I'm telling you. Okay, like that it goes. Carbonic acid is weak acid, therefore it's strong base. No problem. So in the examination, this is one important questioning concept where they'll ask you which among the following is a conjugate weak acid or base. Give conjugate acid for this, conjugate base of that. Something like that. Okay, we'll take it further. I'll just remove all these things. Now, substance capable of acting both as proton donor and proton acceptor are called amphiprotic or amphoteric substances. So we know substance donate proton acid, accept proton base, but certain substances can donate as well accept a proton. Therefore, they are behaving like both acids and bases. Therefore, they are amphoteric or amphiprotic substances. Take example. You see this bicarbonate. Bicarbonate can donate that proton, that hydrogen as proton, and also can accept to become carbonic acid. See here. If it donates H plus, okay, minus H plus, it becomes a carbonate radical. Okay, so now it is donating H plus, no, therefore it is acid. Now you can consider bicarbonate accepting a proton plus H plus, accepting a proton. Then it becomes carbonic acid, H2CO3. In such case, since it accepts a proton, it becomes base. And what about the HCO3 minus now? It is called, therefore, amphoteric substance. Amphoteric substance. So can you people tell me, is there any other substance which can behave like amphoteric from the examples we've seen?
Water.
Bisulfate ion.
Any other substance? Pardon me?
HSO4 minus.
HSO4 minus.
NH3.
Amphoteric. See, this bisulfate. Give me conjugate base of bisulfate. Base remove a proton.
HSO4
2 minus.
Give me conjugate acid of bisulfate.
H2SO4.
Now, from the left hand side, you tell me bisulfate after accepting a proton has become H2SO4. So therefore, HSO4 can be concluded as base or acid for
Base.
this reaction.
Base.
It is base because it is accepting a proton. Now for this right hand side, HSO4 becoming SO4 minus. It is donating. So therefore it is acid. So minus H plus. This is plus H. For this reason, it is conjugate. Amphoteric. No problem. Is there any other substance apart from this?
Water.
Water. Give me conjugate acid of water.
H3O plus.
H3O.
Give me conjugate base of water.
OH minus.
OH minus.
So in this left hand side reaction, is it base or acid?
Base.
Acid.
Acid.
Because it donates a proton. In this right hand side reaction, it is acid or base?
Base.
For the reason that it is accepting a proton. Therefore, it is amphoteric. Okay. So this is amphoteric nature, conjugate acid base theory, the concept of acid and base. So this much is under Lowry-Bronsted theory.
Sir, NH3.
Now, this theory doesn't account again for one of the limitation of even Arrhenius theory, that is this calcium oxide, magnesium oxide. They doesn't accept a proton, but they behave as bases. Okay, Similarly, ferric chloride, aluminum chloride, they doesn't donate a proton, it behave as acids. And why? The theory doesn't give any explanation for that. Based on that theory, we cannot explain. Concept is limited to those. So therefore, we need to consider one more theory which can account the acidic nature, basic nature of those substances which doesn't have H plus ion at all. Okay. So that theory is Lewis theory. Lewis concept of acids and bases. L for lone pair. An acid is an electron pair acceptor. Any substance which accepts a pair of electron is acid. A base is an electron pair donor. Anything which donates a pair of electron will be a base. Now, in the same manner, acid is electron pair acceptor. That means the substance which accepts electron is electrophilic, we say. Correct, no? Electron loving species. Because of that, it accepts a lone pair of electrons. So therefore, according to Lewis theory, since acid is electron pair acceptor, they are also electrophiles generally. Electrophiles are Lewis acids, we can say. Similarly, nucleophiles are electron rich species. They can donate a pair of electrons. So lone pair donor can be bases. Therefore, nucleophiles are bases. You should also correlate like that. Take an example. This ammonia has lone pair of electron on nitrogen atom. When H plus comes near to that, it can bind with ammonia. Then who gives the electron for bond formation? A bond is 2 electrons. H plus doesn't have anything. So ammonia donates a pair of electron to H plus. It doesn't mean that it donates and H plus takes both the electron and become minus. No, no. After donating, the 2 electrons will be shared. Donated by one atom, shared by both the atoms. So it is nothing but a covalent bond with a twist. What is that? In a covalent bond, the bond is formed by mutual sharing up of unpaired electrons. So a covalent bond requires 2 electrons from each bond partner. But here, the 2 electrons required for bond formation is given by one bond partner. As a result, it is a covalent bond, but coordinated by one atom. Therefore, it is also called coordinate bond. A coordinate bond is represented by an arrow mark pointing towards H plus. That means acceptor from donor. So now this is a coordinate bond. A coordinate. Okay. So thus here, which is a base, the one which donates a lone pair. Ammonia donated. Which is an acid, the one which accepts a lone pair. H plus accepted. So acid. Similarly, boron trifluoride is electron deficient species. Why do we call boron trifluoride as electron deficient species? It doesn't have a positive charge. It's a molecule actually, neutral molecule. Anybody? Why do we call BF3 as electron deficient species?
Octet isn't completely filled.
Octet is incomplete. It is electron deficient for the reason that it is having only 6 electrons around central atom boron. And it is ready to accept a pair of electron to complete the octet. So nitrogen of ammonia can give, boron can accept, and thus a bond is formed. This is addition product, adduct. And in this particular case, ammonia is base and boron trifluoride is acid. And a bond formed between them is a coordinate bond. So with this much, we will take remaining part of the concepts once completing worksheet pertaining to these concepts. I have posted in your group the worksheet just before the commencement of class. You can just open that. We'll take up questions from that. Okay. Are you all ready?
Sir, I had one doubt, sir.
Tell me, little louder.
Yes, sir. According to Lewis concept, sir, if it is accepting an electron, then it is acid, no, sir.
Correct.
No base.
Accepting electron is acid.
then most of the non-metals in element stage are acids.
Why do you say all non-metals are this carbon doesn't accept electron?
Sir, most of the.
No, where exactly? No, we can't say that. Sulfur is non-metal. It doesn't accept electron. As a molecule, for example, sulfur trioxide can be taken as acid. Okay, it accepts the electrophile for the reason that sulfur has 6 electrons. Sulfur trioxide becomes more electrophile, electron requiring species for the reason that sulfur is attached to most electronegative 3 oxygen atoms, and thus due to this resonance, okay, so it goes like that. Sulfur at the center becomes positive. It is ready to accept a pair of electrons. Thus it becomes acid. We can't generalize that. For example, P4 is element, non-metal. It doesn't accept. A sulfur by itself is S8 actually.
Yes.
We can't say that.
Okay.
And even oxygen by itself is not electrophile. It's not an acid.
Sir, I got this route because we say metals has lots of free electrons.
Correct. No problem. That is fine. Metals have free electrons, but it doesn't mean that they donate a pair of electrons by themselves. Like sodium is not considered as a base. It donates one pair of electrons. So it all depends on the compound and how exactly things happen in a reaction, considering the overall compound. Okay, right. Not a problem.
Yes.
We'll take up further. Question number 1. Which of the following graphs represent this reaction? Simple question, yet you need to think. Which is the correct graph for this?
Option 1.
Second
Option B.
Option B, sir.
Option B.
I think option C is looking quite good with 3 equal parallel lines like Vibhuti. 1, 2, 3, 4. So there are responses. We'll see now. Option B. There is unanimity in the answer means all are B there. Good, I said. 1B. Kishan Balaji. Okay. So no problem. See here, in any reaction, concentration of reactants decreases, concentration of products increases. Excuse me. Concentration of reactants decreases, concentration of products increases. In the first graph, HI's product concentration can't decrease, no. So second graph is correct. H2 concentration is decreasing, I2 concentration being reactant decreasing, HI increases. So after that, you can see after this point, they are almost remaining parallel. Actually, it should continue. Increase in concentration of HI simply go like that, and H2, I2 decrease like that. Why it is remaining constant? Anybody?
Equilibrium.
They attain equilibrium. Once they attain equilibrium, concentration after that attaining equilibrium will not change. So option 2 is correct. Second, at equilibrium, the rate of dissolution of a solid solute in a volatile liquid solvent is the rate of dissolution of a solid solute in a volatile liquid solvent.
Option C.
Because it is a physical equilibrium between solute and the solution. Always at equilibrium, they have given in the beginning itself. So it should be rate of dissolution and rate of crystallization. Both must be equal because it is equilibrium. Anyhow, okay. Option 3. Okay. Daivik Gowda, any doubts, man? Daivik Gowda. Daivik Gowda.
Sir,
You have raised the hand.
sir, mistakes.
By mistake.
I didn't know. Yes,
You have
sir.
raised
No,
the
I
hand
didn't
for
notice
the
it.
sake of countries. ದೇಶಕ್ಕಾಗಿ ಕೈ ಎತ್ತಿದ್ಯಾ ಅಂತ.
Sir.
ಏನಿಲ್ಲ ಬಿಡು. That's fine, Mr. Dayo. Simply you wished me hi like that. That's fine. We'll take it further. The following is a reversible reaction. Which is a reversible reaction? See, all decomposition reactions are not reversible. They are mostly irreversible.
Option 3.
So calcium carbonate decomposition is reversible for the reason that calcium oxide can again absorb carbon dioxide and give back the calcium carbonate limestone. Backward reaction is favored by increase in the pressure of the equilibrium. Lee-Chatlis principle. Means in which of the following?
3.
If pressure increases, backward reaction.
Option 3.
Yeah.
4.
4.
Option 4.
Option 4, sir.
Okay. Looking at the responses. Option C. Oh no, 4th. I didn't get any answer at all. 4D. Dhanush. Kishan. 4D. Nichin. 4D. Okay. Now, what is that one thing you should remember? Effect of pressure based on Lee-Chatlis principle. The principle says that when pressure increases, reaction will be driven towards decrease in number of moles. Correct, no? Decrease in number of moles to experience less pressure, that's all. If number of moles decrease in the system, pressure applied will be experienced less. So they are asking, when pressure increases, backward reaction has to take place. Upon increasing pressure, if backward reaction has to take place, backward reaction must be associated with decrease in number of moles. Am I right? Decrease in number of moles. In which of the following backward reaction has decrease in number of moles? If you see, in the first case, 2 moles of product become 3 moles of reactants. Number of moles increase. In the second case, 2 moles equal. There is no effect of pressure. No effect of pressure at all. In the third case, 2 moles become 4 moles. Again, that's not actually when pressure increases, forward reaction takes place in 1, 3, whereas only in 4, 2 moles of product become 1 mole of reactant. So when pressure increases, reaction will be driven towards decrease in number of moles. It moves towards backward direction. Backward reaction at high pressure. Okay, so option 4 is correct. No problem. Option 4. Fifth one. In chemical reaction A giving rise to B, the system will be known in equilibrium when?
Option 3.
Option 3.
Option 3, sir.
Vinay, what PA? What pass made? Prahlad says what pass made, and Sudan says flexible. Was it flexing is wrong? I guess you need more concentration than me. What is this, man?
Umed was telling something.
Shall I make it only message to the host?
No, sir. He told wrong answer. So he told me concentrate.
No. Anyhow, I should know the answers. Why everybody should know? It is not an exhibition, no? Correct, no? Now I'll see once again if there is some other unwanted discussions. I'll make it chat with only host. You can flex with me, no problem. Right. I was telling something. Okay. Yeah. So this is the thing, right? In chemical reaction A giving rise to B, the system will be known in equilibrium when. Option
3.
C, sir.
one second. What is this? Okay. Fourth option. Okay. 3. The rate of change of A to B and B to A both are for same. That means rate of forward is equal to rate of backward. Option 3 is. We'll take up next. The Kc for this reaction is 64. If the volume of the container is reduced to 1/2 of its original volume, the value of the equilibrium constant will be 28, 64, 32, 16.
Same, sir. 64.
64 only, sir.
Why?
Sir, why?
Both
Because it,
numerator and denominator it will change, cancel out.
I didn't hear you. I think one was talking. I think Sumedh, tell me.
if volume is reduced to 1/2, pressure increases by 2 times. So therefore, number of moles of reactants will increase by 2 times. Number of moles of products will also increase by 2 times, sir. When you obtain expression for Kc, they'll cancel out and remain unaffected.
Oh, perfect. And I was getting some different answer also. I think Vallabh.
Not me, sir.
Then somebody was speaking about
Kishan, sir. I was
Kishan, tell me,
telling
man.
the same in different.
Tell me, man. I want different answers, man.
Same answer, sir, in different way.
Words, huh? Let me hear
yes,
your
sir.
words, man, please.
It's okay, sir.
Mostly
Sumedh told answer.
Okay. That's right. You are right. See, equilibrium constant value doesn't change when you change the volume. That too, especially this system doesn't have effect of volume at all. Okay. So Kc does not depend upon initial concentrations of reactants and products. If you change the volume, again system will get back to its equilibrium after a while. So numerator denominator values remain the same. The ratio will remain the same. So option 2 is correct. It is again 64. Now people have to take this and work it out. I'll give you 30 seconds. For the reaction, 1 gram mole of calcium carbonate is enclosed in 5-liter container. Kp, equilibrium constant in terms of partial pressure, is given as 1.16 at 1073 Kelvin. Then percentage dissociation of calcium carbonate is. Idea can be percentage dissociation of calcium carbonate means they are asking alpha. Alpha is degree of dissociation. It gives fraction. Multiply by 100. Then it gives percentage dissociation. If you want alpha, you should know how much of calcium carbonate is dissociated. So calcium carbonate dissociated divided by calcium carbonate taken is what is alpha into 100. Now the thing is, how do you find calcium carbonate dissociated? That itself is the question mark. If you know how much of calcium carbonate is dissociated, then only you can find out alpha. Initial amount of calcium carbonate, they have given 1 gram mole. 1 gram mole is nothing but 1 gram molecular mass. Both are same. Okay, I'll also tell you. Calcium carbonate decomposed should be equal to carbon dioxide liberated. So you can find out how much of calcium carbonate is decomposed through calcium carbonate liberated. Now you can do that.
Sir, 6.58. Second option.
Who is this?
Vallabh, sir.
Oh. Anybody else?
10 minutes.
Excuse me? What about remaining people? I say 5C, 7. Still 5C only. Prahlad?
Yes, sir. 1 minute, sir.
30. After 30 seconds, 1 more minute, man. And what about Niti Gandhi, Rena?
6.58.
Huh?
6.58.
6.58 only. What about remaining? Sandra? We'll take it further. The number of moles of carbon dioxide, you can find it out by using PV is equal to RT. Okay, PV by RT equation. So number of moles, pressure, how much is the pressure that they have given? Then how did we take this pressure as 1.16? You can write the equilibrium constant for this reaction expression. I'll write here. Actually, it should be equilibrium reverse. Okay. Now in the numerator, what do you get? So partial pressure of calcium oxide into partial pressure of carbon dioxide divided by partial pressure of calcium carbonate. I'm explaining how come we have taken Kp value as partial pressure of carbon dioxide. For that, I'm explaining. So when you write Kp expression, it will be like this for this reaction. But this calcium oxide is solid. Solids partial pressures will be taken as unity because that doesn't contribute for the overall pressure of the system, right? So therefore, it is unity. Hence, Kp is nothing but what? The equilibrium constant in terms of partial pressure reduces to this expression for the reaction of decomposition of calcium carbonate. Is that okay? So Kp is nothing but partial pressure of carbon. So in that way, Kp value can be used as pressure. And volume 5 liter. R we know in terms of liter 0.0821. This is not 10 to the power, it is 1070. Okay. Excuse me. If you simplify, number of moles of carbon dioxide liberated will be 0.0658. And that is nothing but number of moles of calcium carbonate decomposed. How come? Because they are in the ratio 1:1. 1 mole of calcium carbonate would completely give 1 mole of carbon dioxide. So number of moles of carbon dioxide is equal to number of moles of calcium carbonate dissociated. So what is percentage dissociation? Alpha into 100. Alpha is nothing but dissociated moles by moles taken initially into 100. So come on. 6.5. Very good. Those who have done correctly. I think you people would have simply considered this Kp value as pressure. Did you reason it out like this? No problem. Anyway, you have done correctly.
No, sir.
If it is done, let me know. I'll proceed with the next question.
Done, sir.
Okay, thank you. We'll proceed. So, 8th. For the reaction given here, what is Kc? When the equilibrium concentration of SO2, O2, SO3 are given. So, now concentration is directly given. Just write Kc expression, substitute simplify. Let me know the answer.
Option A, sir.
Yes, sir. Option A.
Option A. What remaining?
12.229.
Okay. All of you are working. It is simple, no? Directly you can substitute and simplify.
Option A, sir.
I'm not getting any response on
Option
chat
A,
box
sir.
from those people who doesn't speak. They only chat. No problem. So write Kc. As per that, the coefficient should be raised to the power. Substitute. And when you substitute, you get the answer. 12.229. No. So option 1 is correct. 9. At 473 Kelvin, Kc for the reaction is 8.3 into 10 raised to minus 3. What will be the value of Kc for the formation of PCl5 at the same temperature?
Option 2.
Why?
It will be reciprocal of that, sir.
Very good. So look at this. There are certain things like, in forward direction, there is some reaction, A plus B giving rise to C plus D. The forward reaction has Kc, equilibrium constant. Then backward reaction will be 1 by Kc. Because products become reactants, reactants become products. So it becomes reciprocal. Correct, no? Similarly, whenever you multiply an equation, Kc is the equilibrium constant for this reaction. If you take 2A plus 2B giving rise to 2C plus 2D, then what would happen? If you multiply whole equation by 2, then the equilibrium constant, new equilibrium constant will be Kc square. If you divide, that means 1 by 2, 1 by 2, or 1 by 3, 1 by 3, then Kc to the power 1 by 3, 1 by 2, whatever. Like that. Is it okay? So that's as simple as that. This is the reaction where they have given is decomposition of PCl5. What will be the value of Kc for the reaction? For the formation of PCl5 means it is backward reaction. Obviously, it is reciprocal you have to take. The reverse reaction, Kc dash is the equilibrium constant, which is nothing but 1 by Kc of power. So 1 by 8 is 120.4348. Option. Next, 10th one. 5 moles of SO2 and 5 moles of O2 react in excuse me, react in closed vessel. At equilibrium, 60% of SO2 is consumed. The total number of gaseous moles in the vessel at equilibrium, that's the name. At equilibrium. So 5 moles of SO2, 5 moles of O2 closed. And at equilibrium, SO2 is formed. SO2 is consumed 60%. And the total number of gaseous moles. They have given SO3. It is the formation of SO3. Obviously, you can understand from the reaction. SO2 when combines with O2, it gives SO3. Write a balanced equation for SO3 formation. And data is given at equilibrium 60% of SO2 is consumed. Then total number of moles were found. Anybody?
8.5.
8.5. Okay. What about remaining?
8.
Pardon me?
8.5. Option.
Okay. Good. Chat.
Yes, sir. Same answer.
Okay. We'll take up next. The solution for this. See, SO2 when combines with O2, it gives SO3. We need to take the data for initial reacted or consumed. You can say either reacted or consumed, and present at equilibrium, remaining at equilibrium, anything. So now initially they only have given 5 mole, 5 mole. Sometimes they'll not give. In such cases, you can take coefficients, whatever there, 2 and 1. But here they have taken 5 mole, 5 mole, and 0 mole of product, because initially reactants will be there, not products. Now after some time, equilibrium is attained. At equilibrium, how much is reacted? They have given 60% of SO2 is consumed, means 60% of 5 is 3.6 into 5. So that's not 3 moles of SO2 is consumed. Now O2 they have not given in the problem, but you can decide, because in the balanced equation, for every 2 moles of SO2, how many moles of O2 is consumed? Half of that, 1 mole. How many moles of SO3 has formed? Same as that. SO2 2 moles consumed means 2 moles of SO3 will be formed. That is the ratio. So how much of SO2 is consumed? 3 moles we just calculated. Half of that will be 1.5. Correct? No? 1.5 moles of O2 will be consumed. So this is dash because reacted is only for reactants. At equilibrium, some amount of SO3 also will be formed. Now, out of 5 mole, 3 mole is reacted. How much is remaining? Therefore, 5 minus 3, 2. Out of 5 mole, 1.5 mole is reacted. How much is remaining? Therefore, it is 3.5. And how much of SO3 will be formed at equilibrium? It is same as SO2 consumed. How much of SO2 consumed? 2 moles is consumed. 3 moles is consumed. If 3 moles is consumed, same amount of SO3 will be formed, 3 moles. So 2, 3.5, 3 is 8. Very good. Those of them. So option 4. We'll take a look. Predict the direction of the reaction from the comparison of QC and KC. Mark the incorrect statement. And don't look at the diagram, just find out the statements. You can find which is incorrect.
Option 1, sir.
Okay. If
Option
KC,
2,
QC
sir.
is less than KC.
Option 2, sir.
Option 2.
Option B.
Option 2, if QC is equal to KC, reaction goes to
Yes, sir.
what
Yes,
method?
sir. Option 2.
Incorrect statement.
Second option are Kishan.
Yes, sir. It is incorrect statement.
Oh, incorrect statement. Okay. So correct for incorrect. That's fine. If QC is equal to KC, reaction goes from left to right. So I think reaction will not go. The person who carries that will go. That's all. Because if QC is KC, it has found Samadhi Sthiti. So that means equilibrium state, happy. It wants to remain for a long time like that. So it is incorrect is option 2. Just everything is right. 12th. For the following reaction, 1, 2, 3, 1, 2, 3 there. Equilibrium constants are given K2, K3. Which of the following relation is correct? That means when you do in which of the following relations, according to which of the following relation, if you follow either multiplication or squaring, cubing, the relations will be correct to one another. One way of doing it is board method. Write KC expression or K1 expression for equation 1. That is product of molar concentration of product to denominator reactants, like that. Write K2, write K3. Compare K1, K2 and do some operation mathematical to get K3 expression same. That is one method. Let's do 30 seconds. Hello? People are there?
Yes, sir. Sir, K3 equal to K1 into K2.
Option 3, yeah.
Option 4.
K3 is equal to K1. Try D. Dhanush. Neeti Gandhi. D.
D, sir.
Where are people, I say? Farzana. D. See, in my last interaction with parents, some of the students have promised that they will be active, they will interact. That's all. That was the last interaction I had. See, I gave the answer. Okay, listen to me. I think Vallabh gave me answer or somebody else. Who gave option 4?
Me, sir.
Me means who?
Prahlad.
Prahlad. Okay. How did you do? The writing the expression you compared, or what is that exactly?
Yes, sir. You told us of that method.
Oh, fine. Now listen to me. One way is that itself. Okay. But another way, you can just look at these reactions. Like the way we used to do SS law problems in thermodynamics, in that manner. Okay. Look at this. In the first equation, CO, H2O is there on the left hand side, CO2, H2 on the right hand side. And in the second equation, methane, water is there, water common. CO, which was there on the left hand side, is there on the right hand side now, H2 common. Whereas in case of third equation, methane common on the left hand side, water, oh, when we add 2 water, oh, could be there. Then hydrogen. So when we add H2 plus 3H2, it gives 4. Oh, the idea is, oh, let us add first 2 equations. Correct? When we add the equations, what happens actually? Common terms will get cancelled. Okay? Anything to cancel? Nothing else to cancel. Methane remains. Water and CO2. 1 plus 3, 4H2. So obviously, this equation, third equation, is a resultant of addition of first 2 equations. And in case of SS law, delta H values will be simply added. If you add equations to get a third equation, in case of equilibrium constant, you have to multiply, that's all. So this K3 should be equal to K1 and K2, as simple as that. Whenever you add 2 equations to get a required equation, then their constant should be multiplied, that's all. This, if you want to analyze, again, you have to do the same thing. You take, once again, at home, you can do this. So K1, you write the expression. K2, you write the expression. K3, you write the expression. Compare K3 with K1 and K2. Do what to get the K3. So then you will get to know, if you multiply K1 and K2, then terms will get cancelled to give it K3. So that means when 2 equations are added, their constant should be multiplied to get the required equation. That's as simple. Is it okay? So just compare equations and do whatever the mathematical process to get that. Is it okay? So let's say this equation 2 were to be reversed. This equation 2 were to be reversed. Methane, water on the right hand side, CO1, 3H2 on the left hand side. Then to get the third equation, what would you do? You reverse the second equation and then add. Correct, no? When you reverse second equation, then it becomes 1 by K2. Correct, no? So reversing makes 1 by K2. Then K1 should be multiplied with 1 by K2. Like that. That is only when It was reverse, given reverse. I think you have understood. No problem. This is somehow easy way of doing it. So option 4 is there. Go to 13. A mixture of 2 moles of N2 and 8 moles of H2 are heated in a lead vessel till equilibrium is established. At equilibrium, 0.4 mole of N2 is present. The equilibrium concentration of H2 will be right, initial reacted remaining. From that you can find out amount of H2 at equilibrium. Then you can calculate concentration.
.6 molars.
1.6 are?
Yes, sir.
Okay. 2, 8. 0.4.
3.2, sir.
3.2 divided by 2.
You have to go one step further. Correct. Okay. I'll take the solution. See, this is the equation, right? N2 plus 3H2 given to 2NH3. How many moles of N2 are taken? 2 moles. H2, 8 moles. Initial number of moles. Now, how much is reacted? Out of 1 mole, let's say X mole reacted. For 1 mole, X mole reacted means for 3 moles, how much will be reacted? 3X. Correct, no? So, if 1 mole combines with 3 moles, 2 moles will be formed. But 1 mole is not combining completely. So, X mole is combining with 3X mole. In the same ratio, how much will be formed? 2X. 1, 3, 2. 1X, 3X, 2X. Same ratio. So, if X is reacted, how much is remaining? Out of 2 mole, X is reacted, 2 minus X is remaining. They have given in the problem 8 moles, not 3 moles. 8 moles initially. How much ever initially taken, but reaction takes place in the same ratio. So, 8 moles minus 3X. So, what is the total number of moles there? Okay, before that, they have given 0.4 mole of N2 is present at equilibrium, right? What is present as per our representation here? Amount of N2 remaining at equilibrium is 2 minus X. How much is that in the problem they have given? It is 0.4. So 2 minus X is 0.4. Therefore, what is X is? 1.6. If once X is found out, you can find out anything in the reaction at equilibrium. Now, H2 moles at equilibrium. How much is H2 mole? 8 minus 3X. X we have found out. So 8 minus 3 into 1.6 is 4.8. It becomes 3.2. Am I right? So number of moles of H2 at equilibrium is 3.2 moles. And this is 2 minus X is 1.6 moles. But they're just asking what is the concentration of H2? What is concentration? It is number of moles by volume. At equilibrium, how many moles of H2 are remaining? 3.2. But what is the volume of the vessel? 2 liter. So it is 1.6. Somebody gave me correct answer.
Me.
Okay.
Who?
If it is done, let me know. Where is Nikita? Nikita is not answering any questions. Shall I move on to 14th question? Done?
Yes, sir.
Okay. We'll take up 14th. At certain temperature, Kp for this reaction is 5 atmosphere. The equilibrium pressure of carbon dioxide at same temperature.
5.
Why? Kp
Because Kp is equal to concentration of CO2.
Very good. So we have done just in one of the problem I showed how Kp becomes equal to partial pressure of carbon dioxide. Because calcium carbonate and calcium oxides are solids, their partial pressures is unit. It is option 15. Which of the following is not affected by pressure change?
Option C.
3.
3, sir.
Why? Because equal number of moles are there. Because 2 moles of reactants, 2 moles of products. When volumes are equal, then pressure will not have any. 16. Chlorine plus 3H2 giving rise to 2ClF3. The reaction delta H is given negative exothermic. The amount of ClF3 will increase by which of the following?
Sir, 1 and 3.
Option 1.
1, sir.
The amount of ClF3 will increase by. Looking at the chat, I don't know, it's not responding. Okay. Option 1. No problem. The amount of ClF3 will be increased. So adding F to reactant concentration whenever it increases. I told you whenever concentration increases, equilibrium moves in the opposite direction. So that means increase out opposite ClF3 increases. Reducing Cl2. Whenever concentration decreases, equilibrium moves towards itself. So decomposition of ClF3 takes place. Increasing temperature doesn't favor because it is exothermic. Exothermic reactions will be favored at low temperature. So if you increase temperature, backward reaction takes place. So what is correct is option 1. 17. At high pressure, forward reaction will be favored in. Again, you have to find forward direction. Which reaction has forward direction, decrease in number of moles?
4.
Exactly. So because as pressure increases, reaction will be driven towards decrease in number of moles. Option 4 has 3 moles becoming 2 moles. 18. For the reaction given here, delta H is minus 2 kilojoules. As per Lee-Chatlis principle, which of the following favors forward reaction yielding more SO3?
A.
ABCD, yeah? Change of catalyst, man.
So not catalyst. A, B, and D.
Huh? Yes, A, B, and D. Second option.
That means again
A, B, and C, sir.
A, B, and C. No, ABD again. Again, you want to change the catalyst, man.
A, B, and C, sir.
You are going to be a scientist, man. You see, change of catalyst, it is not possible unless you have thorough research on that. Okay, you cannot simply change the catalyst. Okay, changing the catalyst can ruin the entire reaction.
Misassumption.
Correct, no?
Option.
So ABC is correct. Catalyst, we can't decide on that. Okay, so once a catalyst is fixed for the reaction, unless and until you have thorough research and analysis and found out a new catalyst for that. And of course, catalysis is one of the evergreen field in chemistry. Okay.
Sir, if we use catalysis for equilibrium reaction, forward reaction and reverse reaction won't have same rate, no, sir?
No. See, we know that a catalyst can influence the reaction to attain equilibrium faster. Correct, no? When a catalyst is used to attain equilibrium faster, you keep removing the product here. So it will try to bring in the equilibrium by producing more and more product. In that way, it helps always. Okay. So a catalyst will increase the yield of product because you are going to remove it. In that way, catalyst will be effective even in reversible reaction for industrial manufacturers. So option 4 is correct. I think it's time up. We'll take up 19th onwards in the next class. So fine. We'll meet for the next class. Thank you. Bye-bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you. Bye-bye.
Thank you, sir.
I'm going to stop in the meeting.